in trying to think about the ways in which machines and human minds or animal minds are both similar and different, a reasonable idea is to take a kind of sample domain for human thinking and to see if we can model it using machines, using computers. Now, there are lots of domains, lots of sample problems that we could imagine, like how do we see, the vision problem, or how do animals navigate, the navigation problem, or how do we make judgments about certain situations. But a reasonable place to start, and in fact, historically, this was a place that cognitive science kind of started, is to look at a fairly constrained, narrow set of problems that humans solve. And the kind of problems that I have in mind are represented here. I'm thinking of things like puzzle problems. Now, why are those good examples to begin with? First of all, the idea is that we're trying to take fairly narrow, constrained, but still interesting problems that people solve, and to see if we can get some ideas about how people solve those problems by trying to model the process using computer programs. Puzzle problems are a very natural start for this. I'll talk a little bit about why that's true. But the kind of things that I have in mind here, you see like Rubik's Cube, or the puzzle at the upper right there is the 1516 puzzle, where the goal is to slide those little tiles. You can only slide a tile into the blank space. So for example, in the 1516 puzzle that you see at the upper right there, I could slide the 14 down into the blank space or the 4 across into the blank space. And you can keep making moves like that, and your goal is to try and arrange the 15 tiles so that they start at the upper left and they're in numerical order, 1 through 15. The puzzle at the bottom right is the rush hour puzzle, where you have little plastic cars and trucks on a grid, and your job is to move the cars and trucks around so that the red car, which you see buried in the mass there, the red car can drive all the way out of the grid through that little gap at the right. That's the goal of the rush hour puzzle. And the moves are that you can move trucks and cars back and forth in rows and columns. And of course, there's the famous, by now kind of addictive Sudoku puzzle. I'm also going to mention another puzzle because I'm going to use it as an example to think with here. Whoopsie. So it's the college student's letter home. It's an arithmetic puzzle. Send more money. And the idea here is that each of the letters in this puzzle each unique letter stands for a unique digit, somewhere between 0 and 9. If you see the letter more than once, like the letter E, for example, that will stand for the same digit throughout. And the result is that this is it's a correct addition problem. So if you add the numbers representing send and more, you get the number representing money. So this is one of these standard arithmetic type puzzles. Oh, I should mention one other kind of interesting constraint on this puzzle. The numbers are written in standard fashion, meaning that you're not going to write a number with a leading 0. So right off the bat, for example, in this puzzle that S and M do not stand for 0. That's one of the things you know. In any event, all these are the kinds of problems that seem like they might be good first examples to think with for modeling human minds with machines. Now, there are strengths and limitations of these kinds of puzzles. First of all, they are characterized by not only conscious, but as I say here, effortful thought. It seems to take effort to solve them. You have to work at solving them. And what I mean by conscious is that at least much of the problem-solving process, perhaps not all of it, but much of the problem-solving process could be vocalized. You could say what you're trying to do. You're aware of what you're trying to do. That's not always the case, as we've seen in thinking about problems. We don't really know how it is that we recover 3 dimensions from 2 when we open our eyes and look at objects in the world. We're not really conscious of that. And there's much that we do, of course, where we have tremendous talents, like being able to tie our shoes or ride a bicycle or walk around a room without bumping into things, where it's very hard to make conscious what it is we're doing. In the case of these puzzles, though, they have at least a substantial element of conscious thought about them. As I say, they're evolutionarily recent, meaning, I guess, animals don't do them. Animals don't seem to be terribly interested in abstract puzzles. So this is something that human beings do, unlike a problem like vision or walking on 2 legs, or which some other animals are able to do, or navigating a space, or things like that. Those are evolutionarily old or venerable problems, and we might look to animals' solutions to these problems in thinking about how to model them. But puzzles are human problems, and in some ways that makes them easier for us to think about, because we don't have to think about a long evolutionary history to this. Whatever equipment we have, whatever talents we have at solving these kinds of puzzles, we've developed pretty recently. They're not especially complicated by things like cultural or affective elements. I say that a little carefully. Naturally, there are some cultural elements to all the puzzles that I've shown. Not all cultures are equally into different puzzles. Moreover, it's not quite accurate to say that there's no affective or no emotional element to these things. You want to solve them. You're curious about solving them. So you do have some interest in solving this. Otherwise, no one would attempt them at all if there was absolutely no affective component. On the other hand, it is fair to say that these are, reasonably abstract, and they're reasonably, not culture dependent. That is, you get the feeling that for many of these puzzles, you could explain them to people from a wide range of cultures, even people who have never seen the puzzle before, and they would understand what the puzzle means. So there's not a strong dimension of cultural or emotional, baggage to these things, which again, you might hope might make them easier to model. They're self-contained, as I say, which is that they don't require a great deal of background knowledge. They require some. You have to kind of understand the ideas of arithmetic, or you have to understand the basic physics of sliding tiles, or perhaps what it means to handle a Rubik's Cube. But nonetheless, these are problems that don't require scads of outside factual knowledge about the world. So all of these things make them pretty good candidates for an attempt to model the human problem-solving process by a machine. How do we solve these problems? How could you get a machine to solve these problems? And those same advantages are also, in a sense, disadvantages. These problems, because they're abstract and because they're fairly narrow, don't partake of some of the qualities that we might also be interested in. Problems that animals also solve, or problems where we find it hard to vocalize or make conscious our solution. So those are especially interesting kind of problems, and we're kind of ruling them off limits for the time being. So we'll look at these. A natural way that when people started to model the human problem-solving process for these kinds of puzzles, a natural way was to think of the problem in terms of what computer scientists call a problem space. And what they mean by a problem space is a graph. I'm not talking about a graph like a graph of a function, rather a graph that consists of lots of vertices, which are always represented by little circles. So vertices are represented by circles, and edges are represented, in this case, by arrows. And the idea is the vertices of this graph are meant to represent particular states of the puzzle. So, for instance, in the 1516 puzzle, a state of the puzzle could be an arrangement of the 15 numbers and the blank space. So some arrangement of the 15 numbers and blank space within that 4x4 grid represents a state of the puzzle. And each state, each unique state, is designated by a vertex in the graph. Edges between vertices represent what we naturally think of as moves in the puzzle. So if we were to move in this 1516 puzzle that I show here, if we were to move the 14 tile one space down, that would change our state from one particular state in the problem space to a nearby state in the problem space. And this is a very general kind of technique for representing puzzle-type problems. It's often used to try to represent other kinds of problems, but it has a natural, affinity. It has a certain natural quality for representing puzzle-type problems. So you could imagine, if you think about this, how you would represent a puzzle like the 1516 puzzle, the Rubik's Cube puzzle, the Rush Hour puzzle. Takes a little more ingenuity, perhaps, to represent the arithmetic puzzle this way, but once you've got the hang of translating problems into problem spaces, there are some natural candidates for those kinds of things too. So a problem space is a kind of good general purpose abstraction for representing a lot of these problems. And once you've decided to think about puzzles in terms of problem spaces, other insights kind of emerge from that metaphor right away. First of all, we could talk about how hard a problem is. What does it mean? We've been speaking and we've thought about this question of what makes a problem hard. Well, one of the questions about a puzzle is it a hard puzzle or an easy puzzle? And one way to reframe that question, not the only way, it's not the only factor, but one way to reframe that question is to think about how big is the problem space? And by that I mean, how many nodes, how many vertices are there? How many distinct states are there in the problem? That's at least a rough measure of how difficult the problem is. It fits our intuition because we kind of sense that if you take a similar puzzle but have smaller or larger versions of it, the larger versions intuitively are going to be more difficult than the smaller versions. You could imagine cases where that might not be true, but still that's our intuition, and it's a good intuition. So the 1516 puzzle is harder than the 8-9 puzzle, where you're moving only 8 numbers around in a 3x3 grid. Presumably, if we made a 5x5 grid, the 24-25 puzzle, that would be harder to solve than the 1516 puzzle. And similarly with Rubik's Cube, they market versions, they actually market a 2x2x2 version, and 3x3x3, and 4x4x4, and so forth. So each of those puzzles, they get progressively harder as the cubes get larger. Why is that? Well, we could actually put a kind of numeric measure to that by saying, how many distinct states are there in each of these puzzles? And our intuition is that the larger the graph, the more the possible states, then the harder the puzzle. Let's take a couple of examples. For instance, in the 1516 puzzle, how many distinct states are there? that'll tell us something about how difficult the puzzle is. Well, I'm making a rough estimate here. In fact, it's not a perfect estimate, but a reasonable estimate as to how big the problem space is for the 1516 puzzle would be to say that, gee, in the upper left corner there, we could have any of 16 distinct things, 15 numbers or a blank. So there are 16 choices for what's in the upper left corner. The tile right to the next, just to the right of the upper side, to the upper left corner, which in this case is occupied by a 5. Once we've chosen one of the 16 possibilities for the upper left corner, there are now 15 remaining possibilities for that tile. And once we've chosen that tile, there are 14 remaining choices for the space which is in this photo occupied by a 12. So it doesn't take a whole lot beyond that to see that the number of possible states in the 1516 puzzle is 16 choices times 15 choices times 14 times 13 times 12. Finally, when you get to the last space, you have only one choice, and that's written as 16 factorial. So there's 16 factorial as a first estimate, 16 factorial distinct states in the 1516 puzzle. In fact, that's not quite right, but I'm not going to go into the details. This is a pretty good estimate. 16 factorial is a big number. It's a lot of distinct states in this puzzle. How many states are there in the 8-9 puzzle? Well, by the same reasoning, there are 9 factorial states in the 8-9 puzzle. That's not a small number, but it's considerably smaller than 16 factorial. And if we wanted to do a 24-25 puzzle, we would need a graph of size 25 factorial, which is a very big number. So our intuition is telling us that the larger the particular version of a puzzle, the harder it gets. And that intuition is matched by what we see in the size of the problem space for each of these things. 9 factorial is not a small number, but it's considerably smaller than 16 factorial, which itself is considerably smaller than 25 factorial. The counting states for the Rubik's Cube takes considerably more work, but again, it turns out to be the case that the 3x3x3 cube has quite a few distinct states. It's a very large problem space, but it's smaller than the 4x4x4 cube, which itself is a good deal smaller than the 5x5x5 cube. So again, the sizes of the problem space get bigger. How about this Send More Money puzzle? How big is its problem space? Well, we can make a pretty good estimate at that too. We'll say that each of these, there are 8, as it turns out, there are 8 distinct letters in this puzzle. S, E, N, D, M, O, R, and Y. So there are 8 distinct letters in this puzzle. By the same kind of reasoning that we used with the 8-9 puzzle, we could say, well, we can assign 1 of 10 digits to S, anything from 0 to 9. Once we've made that assignment, we only have 9 digits left that we could assign to E. Once we've made that assignment, we only have 8 digits left that we could assign to N. So a first reasonable estimate is 10. Actually, it's not quite 10 factorial because we only have 8 letters. So we end up going down to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, which another way of writing that is 10 factorial over 2. So we have 10 factorial over 2 distinct assignments of numbers to letters here. That we may, in fact, want to play with our representation of the problem space, but that's not a bad first estimate anyway at the size of the problem space. And it, too, is pretty big. Okay. The fact that we have at least a beginning metric a beginning way of thinking about the difficulty of a problem is helpful. It isn't the whole story. What makes a problem difficult is not just the size of the problem space, although it's natural that that would be a contributing factor. It may include other things like, well, let's think about this. Once we have a sort of graph representation of a puzzle, we can start to think about some other things about this representation. When we receive a puzzle, like an unsolved Rubik's Cube, or the Send More Money puzzle, or the Rush Hour puzzle with all the cars, sort of scrambled around the grid, when we get that puzzle, we are being given a starting state in this graph. Think of it as one of the distinct states of the graph, and that's where we're going to start. So you've given us a puzzle, and it happens to correspond to this vertex in the graph. Now, our job is to move about the graph so that we can take specific moves from one state to another until we get to a goal state. A goal state is, there may be more than one in the graph, but or there may be just one, but a goal state is a vertex which represents the solved puzzle. So in the case of, say, the 1516 puzzle, there would be one state in the graph that represents the arrangement of tiles from 1 to 15 followed by a blank. That's the goal state. And our job is to find a path in the graph, starting at our start state and moving over edges, because those are legal moves. So we're moving over edges in the graph to get to the goal state. Computer scientists refer to this as a search problem. We're searching a graph, starting at a particular vertex and looking for a particular target vertex, and we're doing a search of the graph to look around and see if we can get to that goal or target vertex. This is a search problem that itself gets us to think about certain algorithms or certain computational ideas that we could employ to do a graph search. And it's the kind of thing that computers are really good at doing. So we've taken the situation this far. We've said, okay, there are certain kinds of puzzles, and we can represent the puzzle as a graph, and we can represent our attempt to solve the puzzle as searching the graph. Now, even in saying that, we're already making some big assumptions. Is this really what people do? Is it really a good model of how people think about these puzzles? Even, again, now we might even think, well, we don't do this consciously, but maybe in a sense, if we're vocalizing our solution, you could make some matches you could make some correspondence between the things that we say we're thinking about and the tasks involved in searching a graph. We could start to explore that. Certainly, we could start to explore writing computer programs to solve these puzzles. But we're not guaranteed when we do that the computer programs are particularly representative of what humans are actually doing when we solve the puzzles. It's not a bad start, though. So we'll continue with our discussion of these kinds of problem-solving models in the next session. We've been talking about using computers to solve problems, and for the time being, the kind of problem that we have in mind is mostly the kind of standard puzzles that we saw in a previous lecture, which is to say, think about things like the 1516 sliding tile puzzle as an example, or Rubik's Cube, or various other kinds of puzzles. Those are, at least to a first approximation, those are the kind of problems that both we as humans are able to solve, sometimes with a great deal of difficulty, and that computers are able to solve because they fit well into the programming style of problem solving. When computers are given the task of solving puzzles like this, as we described, we think of the puzzle in terms of a space or a graph that the computer is going to search. We're going to write a computer program to systematically search a graph which represents the available states of the puzzle. Our initial situation, the puzzle that we're given, is a start state in the graph. And then we're going to move from node to node in the graph, looking as we go, where each move from node to node represents a move in the puzzle, like a twist of a Rubik's Cube or a slide of a tile. But we're going to move from node to node in the graph, searching in some systematic way for the goal state of the puzzle. Now, there are many, many techniques in computer programming for graph search. There are a few basic techniques, and I'm going to describe a couple of those today, but one can spend a tremendous amount of time studying the ins and outs of searching graphs via computer. For our purposes, we're only going to describe some major ideas, but of course there's much more detail that you could go into if you're interested. To begin with, we're going to think of searching our puzzle graph or searching our problem graph in terms of what are called weak methods. Now, they're called weak methods not because they're useless or not helpful, but because they don't assume any real knowledge of the problem beyond the problem space description. That is, once you've framed the problem in this, terms of a graph, you can use weak methods to try and find a solution, a goal in the problem. Let me be a little specific. Imagine we're doing something like solving the 1516 puzzle. We represent our initial state of the 1516 puzzle. I'll just do this one time so you could kind of see what a state is supposed to mean. So imagine putting in numbers in each of these little squares, and there's the empty space. So our initial state of the puzzle is represented by this node, and everywhere that we can get to in one move, that is one sliding tile, is written as a new node. In this case, there are 3 next moves because we could move this little tile in here, or this one up here down, or this one below upwards. So there are 3 next moves that we could go to. From each of those, we could go to still other states of the puzzle. I don't know if 3 is the right number of arrows to be drawing here. Maybe I could draw 2 in one case or 4 in another. But in any event, think of this as the start state of the puzzle. These are all the states you could get to within one legal move. The next layer is all the states you could get to within 2 legal moves. The next layer is all the states you can get to using 3 legal moves, and so forth. Now, I'm sweeping some stuff under the rug here. For one thing, it's clear that for many puzzles, this graph format will be enormous. We'll deal with that. I mean, that's part of the difficulty of solving puzzles in general. I've structured this graph in a form that computer scientists call a tree, meaning in this case, there's more definition to give, but from our standpoint, what it means is there is a designated state called the root, which is where we started the puzzle, and then there are branches from the root going to all the moves, all the places, the states of the puzzle we can get to within one move. And then from these, there are branches to all the states we can get to via 2 moves and so forth. So the structure of this graph will look like a spreading tree as it moves downward, as we go to 4 and 5 and 6 moves and so forth. Okay? So with this in mind, searching a graph becomes searching a tree. And the standard weak methods, the 2 that are always introduced first in this context, are called depth-first search and breadth-first search. Depth-first search, we could go into much greater detail, but I'll just kind of give you a informal description of depth-first search. Depth-first search means that you follow a certain path of moves. Imagine that you sort of make one move, and then you make a second move, and a third move, and a fourth move, and so forth. You're following down in depth a particular path to trying to solve the puzzle. If you run out of options, or you reach a dead end, then you move back up to the last place that you were able to make another choice and try that. So qualitatively, the feel of depth-first search is that it looks down a tree for a long way. If it runs into a dead end, it backs up and tries some other branches. If those don't work, it backs up some more and tries some other branches. So you get this pattern of working up and down the tree until you find, hopefully, a solution to your problem. Breadth-first search, by contrast, is a systematic way of searching a tree in which you first look to see if this is the goal state. If not, you look at all the states you can get to within one move and see if they contain a goal state. If not, you look at all the states you can get to in 2 moves, see if they contain a goal state, and so forth. So breadth-first search is almost like reading the tree across as a text. You're seeing if the goal state is here, then in the next layer, the next layer, the next layer. These, as I say, these are methods that don't depend on knowing much about the puzzle other than the fact that you've set it up as a tree. They're useful methods, and they're often the foundations of more complex methods, but they're also highly flawed in the sense that there are different reasons why either one can prove to be a huge problem. In the case of breadth-first search, we've noted that problems have this nasty habit of expanding, sometimes exponentially. And so if you look at a tree like this, you might see 1 node in the top layer, 3 nodes in the second, 9 in the next, 27 in the next, 81 in the next. And if your solution takes something like 25 moves, you will be looking at an extraordinary number of, an unwieldy number of problem states in this tree. Depth-first search runs into other problems in that sometimes a problem space is infinite, and you may find yourself, for example, looking down a pathway of potential moves that never ends. The 1516 puzzle is not infinite, and so you can set up depth-first search so that it will eventually find a solution. But it still may take an extraordinarily long time. As I say, weak methods are called that because they assume very little knowledge. In that respect, they're not very human-like. To some extent, we do things when we're solving puzzles that can look a little bit like depth-first or breadth-first search, but in their extreme versions, we don't really think that way. You may reflect on the way in which you solve some puzzles and see if there are some elements of your own problem solving that feel either a little bit like breadth-first or depth-first search. More human-like. That is, as we're moving from machine-solving puzzles to minds-solving puzzles, there are machine techniques that feel a little closer to the human style. They're still not perfect in every respect, but they feel a little closer. One is called hill climbing, and the idea is you think of the problem space as laid out on a terrain in which the better, the closer you are to a solution, the higher the terrain is. So in effect, what you're trying to do is wander around the terrain on this graph, looking for the highest peak. Think of the solution to the problem as a mountaintop that towers above the rest of the graph. And so you're moving around on this terrain looking for the highest peak of the graph. Now, hill climbing is not a bad idea if in moving around the graph you're always trying to move upward. So it's as though you were walking on a terrain, a geographical terrain, and always seeking to move upward as you go. In certain situations, that can work very well. In other situations, you may run into problems where, for example, you may be looking for the highest peak in your graph, and you may run into a situation where there are two standard kinds of problems. These aren't the only ones. But one problem is you move to the top of a little hill, and it is not the ultimate solution to the problem, but every move that you can make from that little hill seems to be a move downward. That can be an issue because you don't really know how to, you're stuck. You're at what could be called a local maximum, meaning you've moved to a place where every move from that particular situation seems to make your situation worse. However, this little hill is not the ultimate solution to your problem, so it's hard to know where to go from here. Another kind of problem with hill climbing is that you may be on extraordinarily flat terrain, a plateau, in which there's no clear reason to move in one direction or another. Those are the kinds of problems that come up with hill climbing. But in some respects, it feels a little bit closer to a human kind of reasoning. We're looking for a peak, and in order to find that peak, we'll see if we can find it by just moving upward wherever possible. Best first search is an idea where you're searching a tree, but every time you consider the next move, you look to see which move appears to be the best. Now, notice that this idea, just like hill climbing, assumes that you have some metric for the goodness of a state. It assumes that when you're considering these three different moves, you have a reason to prefer one to the other two. That represents knowledge about the problem. So the only time you could use an idea like best first search is when you feel that you can, rank order moves in the puzzle in a sensible way. I'm going to describe yet another technique called means-ends analysis, and this has an interesting history in cognitive science because it was one of the early techniques for problem solving studied both in human beings and in writing computer programs to solve puzzles. It too does not work in every situation. In fact, it is fairly constrained in the kinds of situations that applies to, but it's readily representable in a computer program, and it applies to certain kinds of puzzles or problems that we sometimes run into. I'm not going to give you a coded version of means-ends analysis, but I'll try and give you the flavor and prose. This was investigated early on, by the way, by Alan Newell and Herb Simon in the early years of artificial intelligence. So the basic idea behind means-ends analysis is you are in a particular state of a puzzle or problem. You want to get to a goal state. You first look at what appears to be the biggest difference between you and your current state and the goal state. If you can do something that will reduce that difference right off the bat, you do it. On the other hand, if you can't find anything to do to reduce that difference, you see if there's something else that you can do that will reduce the difference between your current state and a position in which you can attack the biggest difference. So there's a recursive element to this means-ends analysis. Let me say this again. The idea is you look at your current state, you look at the goal, you say, what's the biggest difference between me and the goal? If I can attack that right now, let me do it. If I can't, let me pose a new problem, which is getting to the point where I can attack it, and try and solve that problem by means-ends analysis. It's an inherently recursive idea, and it's in coded form, it's actually a beautifully elegant program. It's close to certain kinds of puzzles. I've always felt that the rush hour puzzle, where you're trying to maneuver that red car, can I point to it here? Yeah, the red car, you're trying to maneuver it out of the grid. And the only way you can do that is by moving cars that are in front of the red car so that you can eventually get it out of the grid. So when you try to solve the rush hour puzzle, you find yourself saying things like, if I could move the car directly out, I would do that. But I can't because there are a couple of cars in the way. So my new problem is getting those cars out of the way. Let's see if I can get those cars out of the way. If I can't, it's presumably because they're being blocked by still other cars. So let's see if I can get those out of the way. That's a technique for solving rush hour, at least for some puzzles, and it has the flavor of means-ends analysis. Now, for computer scientists, when we try to write algorithms for searching a problem space graph, there are standard issues that always come up. They're not exactly the kinds of issues that always come up when we think about us as human beings trying to solve problems. But they resonate a little bit, at least, with some of the human issues. One problem is we'd like to have a search technique that is guaranteed to find a solution if there is one. So taking, for example, our 1516 puzzle, if there is a solution, then because it's a finite graph, if we implement either depth first or breadth first search in a reasonable way, and again, I'm sweeping a little bit under the rug, but if we do this with reasonable cleverness, either of those two weak methods is guaranteed to find a solution, assuming there is one. Some search algorithms may not be complete in that sense. They may be interesting for other reasons, and they may be promising, but they may not be guaranteed to find a solution. Obviously, if we had an algorithm that was guaranteed to find a solution, that's of some value to us. A second issue is, how long is this going to take to run? If we are going to find a solution, is it going to take a minute, a year, a century? That, too, is an issue about creating these search algorithms. We may have a vast problem space, and searching that problem space for a solution, we may be guaranteed to find a solution, but it may take years, in which case we have other problems on our hands. We might want to, for example, find an approximate solution, or see if we can find a better search algorithm that will take less time. Similarly, in computer science, along with time, there are space considerations. So memory is a good deal cheaper than it used to be, but it's still finite in any computer. And so we don't want to write a program that will take an infinite or an astronomical amount of memory. We would like to write a search program that will only use up a relatively small or measurable amount of memory as the algorithm runs. That too can sometimes be a problem. Finally, there's an interesting issue that deserves mention here. Our algorithm may find a solution, but it may not find the best solution. Take, for instance, solving Rubik's Cube. You may be given a scrambled Rubik's Cube, and it may turn out that the quickest solution to this scrambled Rubik's Cube takes 4 moves. You could unscramble it in 4 moves. Your computer program, your search algorithm, finds a solution to the Rubik's Cube, but it takes 20 moves. Well, maybe you don't care. I mean, maybe all you wanted was a path to solve the Rubik's Cube. But this could conceivably be a meaningful issue to you, where not only do you want the program to find a solution, you want it to find, by some measure, the best solution. These are all things that computer programmers care about when we write search algorithms, and they have resonance with certain kinds of human problem-solving activities, but the connection is not always straightforward. There are other kinds of issues about solving problems that are worth mentioning. I don't want to finish the discussion of solving problems quite yet, but in this particular session or lecture, I would like to just talk about 2 additional issues about thinking of problems in this search space formalism. One is that the way that human beings solve problems or puzzles seems to involve more than just search, or more than just immediate search. It seems to involve other kinds of things, like looking for patterns in problems that we're solving. Let me give you an example of what I mean by that. This is a famous experiment that was done by Chase and Simon in the early 1970s. And here was the nature of the experiment. It was actually a memory experiment. They were looking to see, to ask a question about the memories of chess experts versus chess novices. And it has sometimes been suggested that one reason to study chess is that it'll improve your mental functioning, perhaps even improve your memory. So the Chase and Simon experiment was designed to test that question. Do chess experts have better memories than chess novices? And the way that they did this test was they showed both chess experts and chess novices sample chessboards with pieces on them, like the one in this slide. So they showed both the expert and the novice a chessboard like this one with pieces upon it, and they only showed it to them for a limited amount of time, matter of seconds, I believe. Then they asked both the chess novice and the chess expert to see how well they could recreate the board from memory. Okay? Now, in principle, if a chess expert has a far better memory than a chess novice, he or she will be able to recreate the board much more accurately. Here's what they found. It was quite interesting. What they found is that if the chessboard had an arrangement of pieces that was taken from an actual game, from a real gameplay, then indeed the chess expert was much, much better at recreating the board than the novice. If, however, the chessboard just had a random scattering of pieces in various places, the kind of situation that you would never actually see in a real game, then the chess expert and novice were equally bad at recreating the chessboard. They were comparable, okay? The meaning of the interpretation of this experiment is that the chess master has better memory of real chessboards because when he or she is playing a game, they're not just interpreting the game position as a random collection of pieces, they're interpreting the board in terms of larger concepts of chess play, maybe a pawn arrangement, or whether a king has been castled, or who's getting control of the center, or which pieces are threatened. Those are larger scale notions that inform the way that a chess master looks at a board. They're not available to a chess novice. But when a chess master has to recreate a board, he or she is thinking in terms of these larger scale patterns. That too would be applicable to other kinds of problems where, for example, this has been studied in problem solving in physics, where physics experts are able to look at a problem and grasp certain concepts in the problem, larger patterns that are unavailable to the novice. So that's one issue. We would like, if, as we're thinking about writing machine models of problem solving, we would like to think of ways of grasping higher level patterns about certain problems. Another issue, and this is the last one I'll talk about, is that sometimes it's tricky to determine how to think of a problem space. This is a fantastic little puzzle that way. And because it's a fantastic puzzle, I'm going to describe it to you at enough length so that you can think about it. Here's the idea. If you take a standard chessboard, 8x8 chessboard, and you're given the problem of tiling that chessboard with 32 dominoes, that isn't very hard. What you could do, for instance, is take the chessboard and then place 4 dominoes in each row, or 4 dominoes in each column. When I say tile the board with dominoes, what I mean is place the 32 dominoes on the 64 squares in such a way that the dominoes are covering the entire board and they don't overlap. And there are all kinds of ways of doing this, and you can see that there are all kinds of ways of doing it. That, as it turns out, is not a hard problem. Now we set a slightly variant problem, okay? This is called the mutilated chessboard problem. We take away the opposite corner squares of the chessboard, leaving a board with only 62 squares on it. So as you see in the slide here, we've taken the upper left and the bottom left square out of the chessboard. Now there are 62 squares left in the chessboard. And the question is, can you tile this mutilated chessboard with 31 dominoes? So can you take 31 dominoes and lay them out on this chessboard in such a way that they'll cover the entire thing and they won't overlap? Now, this is interesting. When I pose this question to computer scientists, what they often do is they imagine writing a program that will systematically search all the possible ways of laying down dominoes on a 62-sized mutilated chessboard. And they'll try to imagine ways of doing that systematically and trying every possibility. You could do that. I mean, such a program could be written. However, there's an immediate way of seeing that the answer is no, it cannot be done. And the reason for that answer, when you think about it, is this. Every domino that you place on this chessboard has to cover 1 black and 1 white square. Whether you place it vertically or horizontally, it's going to be covering 1 black and 1 white square. Therefore, if we put down 31 dominoes, they should cover 31 black squares and 31 white squares. In this mutilated chessboard, however, we've subtracted 2 white squares. So the board as left has 32 black squares and 30 white squares. Once we place 30 dominoes, therefore, we'll have covered all the white squares and there will still be 2 black squares left over. Can't be done. This is, in fact, it's what could be called a parity problem, P-A-R-I-T-Y, a parity problem, because every domino has to reduce the size of the available puzzle by 1 black square and 1 white square. And so we can't do that. In order to see that, though, we have to think of the problem space in different terms. The sort of automatic brute force way of thinking of the problem space would lead us to this vast search algorithm. A different way of looking at the problem space would lead us to an immediate solution. So this is an interesting instance of the limitations of the sort of unthinking problem space approach. In order to look at a problem in a creative way, you may have to think about the problem space in ways that are non-obvious. For many problems, computers are extremely good at solving them. They're good models of how to go about solving problems. And in some cases, they solve certain types of puzzle problems more effectively than people do because they make use of a problem space representation. They're systematic in search, and they can often solve certain kinds of what I might call stereotyped puzzle problems much more quickly, and in some cases, more effectively, more quickly, and finding optimal solutions in ways that people find difficult to do. But not all problems have this flavor of being able to be translated into a problem space. That is to say, some problems are difficult in interesting ways, both for people and for machines. And it's interesting to take a look at these kinds of problems, both because they compel us to ask questions about our own techniques for solving problems, and also they compel us to look at computer programs and think about new and creative ways of implementing problem-solving strategies in computers. So rather than stick with the kind of tried and true problem space approach, let's look at some examples that in one fashion or another challenge that approach. Here's an example. We've talked about, if you've watched some of the previous discussions, we've talked about techniques by which computers can solve certain kinds of puzzle problems like Rubik's Cube, or the famous 1516 puzzle, or the rush hour puzzle, other kinds of things like that. This is another sort of puzzle that you can get at a puzzle shop. These are topological puzzles. They come in various forms, rings or wires or things like that. In general, the structure of these puzzles is that you have to take them, they're physical objects, and then you have to manipulate them in some way to separate pieces or reconnect pieces. And they're often quite difficult. It's an interesting question to ask how you would get a computer to go about solving a problem like this. It doesn't seem to fit terribly naturally into the problem space formalism. That is, it's often not clear when you pick up one of these puzzles what constitute the distinct states of the puzzle and what constitute the legal moves. In a case like Rubik's Cube or the 1516 puzzle, it's very clear what the distinct states of the puzzle are. They are the arrangements of the cubes or the arrangements of the tiles in the box. And you can pretty much say what it takes to make a distinct move. Slide a tile in the 1516 puzzle, or rotate one plane 90 degrees, counterclockwise or clockwise in the case of Rubik's Cube. All well and good. With a puzzle like this, though, it's a little tricky to say what are the distinct states. If I take one of these objects and move one of the rings just by, say, half a degree in space, just rotate it around say, a vertical axis. Is that a new state of the puzzle? Have I executed a legal move? It really seems that when you look at puzzles like this, the difficulty, the essential difficulty is finding out what the states are, what constitute the meaningful states of the puzzle, the positions of the rings, and usually from that point the moves are not so hard if you know what the states are. But knowing the states is the difficult part of this. So this is a kind of puzzle that challenges our usual notion. Thinking about how to get a computer to solve a puzzle like this. Some people are exceptionally good at it, but thinking about how to get a computer to solve a puzzle like this would be a really interesting challenge. There are other kinds of problems that are, in a sense, kind of standard problems. They show up in math books, or they show up in mathematics exams, or they show up in interviews for tech companies. Often these are problems that require a certain amount of creativity and flexibility to solve. If you've ever taken one of these sort of, math Olympiads or Putnam exams or things like that, then you know that problems of this sort can be quite challenging. They may take you, assuming you can solve them at all, they may take you days to solve. They may take a long time to think about. And again, it's hard to see how they could be easily translated into the problem space formalism. So here's an example I got from a wonderful book called How to Solve It, Modern Heuristics. In a moment, we're going to see another book called How to Solve It, but this is a newer book with a similar title. And I'll just read out the puzzle. Mr. Smith and his wife invited 4 other couples for a party. When everyone arrived, some of the people in the room shook hands with some of the others. Of course, nobody shook hands with their spouse, and nobody shook hands with the same person twice. After that, Mr. Smith asked everyone how many times they shook someone's hand. He received different answers from everybody. And the question is, how many times did Mrs. Smith shake someone's hand? So it's a kind of well-done puzzle, because kind of like, in this sense, it's a little bit like Rubik's Cube in that it's well constructed. The way that it's written is intrinsically sort of curiosity provoking. It's like you're reading this puzzle and then you get to the final question, and who even mentioned Mrs. Smith up until this point? All we know is that she's married to Mr. Smith, but there doesn't seem on the surface to be any information about her. But this is a well-formed problem, and you can solve it. I don't think I'm going to solve it right here on screen. I will let you ponder this. But the kinds of techniques that you would use to solve a puzzle like this were described in a wonderful book that came out in the 1940s by the mathematician George Polya. It was called How to Solve It. It's still in print. It's been reissued many, many times. It's a classic, and I couldn't recommend a book more highly. There have been follow-ons to this book along similar lines. That is, books that also talk about problem solving in this way. They often have new contributions to make, but this is a great book to start with if you're interested in the art and craft of solving problems of the kind that I just showed. Now, Polya, I don't know that he invented, but he certainly popularized the word heuristic, meaning a rule of thumb, a strategy to try in solving a puzzle or a problem. Not guaranteed to solve the puzzle, but often helpful, often the kind of thing that you should have in your bag of tricks, that you should have in your repertoire. And some of the kinds of heuristics that he mentions are things like, if you see a problem like the one about Mrs. Smith, do you know a related problem? Maybe if you know a related problem or one that seems similar, and you've already solved that, maybe that solution will help you with this one. Or did you use all the data in the problem? Did you make use of all the things that were presented in the problem? That's a feature, in a way, of artificial problems like the Mr. and Mrs. Smith problem. It's In the real world, sometimes we're faced with problems where we may get extraneous data. We may get data that we don't have to use. But in these sort of well-formed math exam type problems, they play fair. And if they give you data, then presumably they're giving it to you because it's going to be needed to solve the problem. Once you solve it, can you use the answer for a related problem? In the case of the Mr. and Mrs. Smith problem, the advice of drawing a figure, I think, is especially helpful. If you draw a figure, just sort of doodle out a figure that you think might help you solve this problem, and it may do very well. And then Polya mentioned some other kinds of typical strategies of proofs, like reductio ad absurdum, or induction, or decomposing the problem into subproblems. Dimensional analysis is a very helpful technique for solving physics problems, where you can just reason about the dimensions of the quantities involved. But in any event, these are sort of good basic techniques for finding proofs or solving problems and so forth. Some of these, I think, are extremely useful for, at least, as I say, at least the draw a figure piece of advice is extremely useful for thinking about the Mr. and Mrs. Smith problem. There are other kinds of problems that I think are interesting to think about in this light. And again, they lead to new ideas about how you would program a computer to solve a problem like this. So here's, maybe you could call it a physics problem. It's a problem about objects in the real world. So imagine, you could actually try and do the experiment if you want. But before you do the experiment, think of this as a problem that you can solve in your head. A kind of thought experiment. So imagine two quarters side by side, as shown in the picture here. And now you take the quarter at the right, the one which has the head side up, and without slipping, carefully you kind of roll it around. So I could reach here and roll this quarter around the quarter with the tail side up. The tail side up quarter remains stationary the whole time. So once you've rolled this head side up quarter to the opposite, to the left side of the picture, which way will George Washington be facing? Now, that's an interesting question. And the way that we tend to solve questions like this is through, well, at least the way that I would try to solve a problem like this is through a kind of mental imagery, a kind of dynamic mental imagery that executes a sort of animation. That's a very different kind of programming than the programming that would be involved in trying to represent this as a problem space with moves. To solve a problem like this, you would want to, certainly to write a program to solve a problem like this, you would want to get a computer to be able to take sample animations or sample pictures and animate them in realistic ways to get an answer. That would be, and that represents a certain kind of research in computer programming, but it represents a really interesting new way of linking human problem solving with machine problem solving. Again, should I give you the answer to this? No, I'm not going to give you the answer to this. What I would say is you should try and think about this problem in your mind and then see if you get an answer by trying the experiment on the desk with two quarters. Here's another, this is a more straightforward physics problem. So this is a kind of physics problem that you might get in an introductory physics class. So imagine you've got one of these, physicists apparently love these frictionless tracks and elastic collisions, meaning that energy is conserved and momentum is conserved and so forth. So imagine that you have a frictionless track, a ping pong ball rolling to the left, or rolling, it's rolling to the left, my left, at 1 centimeter per second, and a bowling ball is rolling to the right at 1 centimeter per second, and they're going to collide, and then after the collision, they will have new velocities, okay? So totally elastic collision. Now, I don't even know if these are realistic numbers for ping pong balls and bowling balls. I think a ping pong ball is well over 8 grams, but let's just say for the sake of argument that the ping pong ball is 1 gram in mass and the bowling ball is 10,000 grams in mass. So now you have all the information that you need to solve for the final velocity of both the ping pong ball and the bowling ball, if you use the fact that energy is conserved and momentum is conserved, overall momentum is conserved. Okay, well, you could do it that way. It would take a fair amount of algebra. There's a much more straightforward, a little bit approximate, but much more straightforward way of thinking about the problem. I won't go through the numbers for it, but think about it in these terms. You have the ping pong ball. See if I can draw this out. Oops. You have the ping pong ball. Oh, I wish this wouldn't happen. Hold on. Here we go. You have the ping pong ball going off like this and the bowling ball going off like this, and this is 1 gram and this is 10,000 grams. Okay? And they're about to collide. Now, think of it from the physical standpoint. From the viewpoint of the ping pong ball, the bowling ball is much, much bigger. If you were kind of riding on the ping pong ball, it would feel to you as though you were smacking into a wall. So if the ping pong ball were just smacking into a wall, a stationary wall, then we know that, well, in this case, the wall is not going to change its velocity, but the ping pong ball, with energy being conserved, would move off at 1 centimeter per second in the opposite direction after the collision. In other words, if you think of what's going on as a ping pong ball at 1 centimeter per second colliding with a massive wall, it'll just bounce off and go at the same velocity. Well, this situation is kind of the same if you think of it from the ping pong ball's point of view. So one way to reason about this is to reason from the frame of reference of the bowling ball. Imagine that you are in a frame of reference in which the bowling ball is stationary. So you're in a frame of reference that is moving 1 centimeter per second to the right, but in that frame of reference, the bowling ball is stationary, and the ping pong ball is headed for you at a velocity of 2 centimeters per second. After the collision, the bowling ball will still be stationary, essentially. Yes, it will have a little velocity, but a teeny one. And the ping pong ball will be going off at 2 centimeters per second to the left in this new frame of reference. So using that kind of thought, you can solve a physics problem like this. But the step of being able to see that you can make that approximation is the interesting thing here. That is to say, what's interesting is not the numerical solution. What's interesting is looking at a situation like this and seeing that you can get a quick, if not perfect, answer by making a little change in the way you represent the problem. That's an interesting kind of human problem solving. And again, trying to get a computer to be able to do this kind of problem solving would be a creative act. This would take new kinds of directions in computer problem solving. Finally, you've already kind of seen this slide by accident a little bit, but now I'm going to unveil it, okay? So this is a wonderful problem from William Poundstone's book, Labyrinths of Reason. And there are a number of problems like this, where you see problems like this, and this is actually, in a sense, it's a well-formed problem. That is, there is an answer that you can give to this. So let me just read this out. A man gets an unsigned letter telling him to go to the local graveyard at midnight. He does not generally pay attention to such things, but complies out of curiosity. It is a deathly still night, lighted by a thin crescent moon. The man stations himself in front of his family's ancestral crypt. The man is about to leave when he hears scraping footsteps. He yells out, but no one answers. The next morning, the caretaker finds the man dead in front of the crypt, a hideous grin on his face. And the question is, did the man vote for Teddy Roosevelt in the 1904 US presidential election? Now, this is a weird problem, but there are a number of problems of this form. They're fun. You have the information to give a cogent answer to this problem. Unlike the kinds of problems that Polya talks about, there is a fair amount of extraneous data here. There's stuff that is there to, not exactly to lead you astray, but stuff within the story that is not relevant to the solution of the problem. There's a little bit that is relevant to the solution of the problem. Even then, solving the problem requires a certain amount of background knowledge of a kind that not everybody has. But in other words, to answer this problem in the way that is intended for these kind of problems. And by the way, if you have, I'm not going to give you the answer again, but if you have some gamesmanship about this kind of problem, you kind of sense that the answer must be no. He didn't vote for Teddy Roosevelt, but there's got to be something in the phrasing of the problem that indicates why the answer is no. Like either this had to take place at a different time, the guy couldn't have been alive in 1904, it's taking place outside of America, so he couldn't have voted for Teddy Roosevelt, etc. So there's something going on in the presentation of the problem that is telling you no, because it's almost, I find it difficult to imagine how this information could prove that he did, could prove that the answer is yes. So you kind of know the answer is no, but why the answer is no is tricky. Anyway, solving a problem like this requires a lot of background knowledge. It's not and for problems of this kind, the background knowledge may come from all over, may come from all kinds of different domains. Moreover, you have to sort of search within the narrative to see what things are relevant to solving the problem. These kinds of problems that we've talked about in this discussion today are all problems that represent challenges for computational versions of problem solving. When we talk about machines and minds, different ways and similar ways in which machines and minds operate, these are interesting objects to think with, because to get a computer to approach problems like this, and in different cases people are working on topics related to these ideas, but to get a computer to approach problems like this requires interesting, creative, new approaches beyond that of the problem space. One of the more pointed comparisons between the ways that people think and the way that machines think has to do with debates and discussions around the theme of logic. Logic is a very broad term. Logic in general, it actually refers to a tradition of thinking that goes back to at least as far as Aristotle, who wrote about logic. Aristotle's portrait of logic centered around syllogisms, patterns of reasoning like all men are mortal, Socrates is a man, therefore Socrates is mortal. You've probably heard these kinds of syllogisms before. Syllogisms were kind of the mainstay of logic for a very long time, but logic over the past couple of centuries has expanded and changed and grown more expressive in a lot of ways. The the discussion having to do with machines and minds often centers on this idea that machines are particularly logical, or the ways in which computers can think is especially logical. That's a complex question. We can program computers in ways that are less sort of rigidly logical than we often associate with computational information processing or thinking. That is to say, we can program computers so that they can behave a little less rigid a little less rigidly, a little less formally, a little less strictly according to the rules of established logic. Nonetheless, logic fits well. It sort of lends itself to computational implementation, at least in a lot of cases. So let me begin, not quite at the beginning, but with the beginning of modern logic. So I mentioned discussions of logic go back to Aristotle. For our purposes, modern logic starts with a book by the English mathematician George Boole called The Laws of Thought. It's a very difficult and challenging book, in part because Boole was thinking out all these ideas on the page. So it's not the best introduction to ideas of logic. In fact, in Boole's book, he kind of mixes different formalisms from things that today would be referred to as Boolean logic, that is, logic having to do with ones and zeros, propositional logic, that is, logic based on the idea of manipulating true or false sentences, and finally set theory. All of those things are kind of mixed in Boole's book, and that makes it rather difficult to read. The explanations often kind of shift from one domain to another. All those topics are in fact closely related, but Boole's treatment is difficult to read. So I wouldn't advise picking up Boole's book to learn about propositional logic or Boolean logic or set theory. I wouldn't advise reading it for that purpose, but it's an interesting book to read once you have learned something about the modern formalisms of logic, to go back and see where those ideas began. In any event, we'll focus for the time being on propositional logic. So in propositional logic, the idea is that letters or symbols stand for entire propositions that can be true or false, like 5 is a prime, that happens to be true. Paris is the capital of Italy, that happens to be false. Think of P and Q and R and other kinds of symbols here as representing declarative sentences, the easiest way to think about them, that could either be true or false, but not both. Now, propositional logic allows you to reason with sentences of that kind by combining them with what are called connectives, like and or, if, then, and then doing certain kinds of fairly straightforward reasoning using the propositions and the sentences that you've asserted. I've just got one teeny example here. I'm not going to go into propositional logic in depth. If you haven't seen it, you don't need to know it in depth for the purposes of this discussion, but this is the kind of reasoning that gets done in propositional logic. So you have a bunch of assertions, you have a bunch of sentences that you say are true, we're going to treat as true, and then from those sentences, we will see what else we can deduce that could also be true, that should also be true. So in this case, we've asserted 3 things. Number 1, we've asserted if P or not Q, that is to say, if it is the case that P or not Q, then R. And again, what the meaning of P and Q and R should be depends on the use of propositional logic. When you're using it, you might substitute for P and Q and R things that make sense in this particular form of reasoning. For our purposes, we're just leaving these as uninterpreted symbols. We're just stating as a given that if P or not Q is true, then R is true. We also are given, we are told, that Q is true and that P is true. From those three sentences, we can deduce still other true statements. For example, sentence 4 tells us, since we know that P is true, we also know that P or not Q is true. We didn't even use sentence 2 in this case, but from sentence 3, we can deduce that since P is true, it must be the case that P or not Q. Now, one thing I should mention is that in standard propositional logic, or is interpreted as what we would call inclusive or. P or not Q is a true statement if P is true, if not Q is true, or if both are true. So the or here is inclusive as opposed to the exclusive or, which is usually written X or, and which is only true if one or the other but not both are true. In this case, it happens in the case of sentence 4, it happens to be the case. We happen to know that P is true and not Q is false. Still, P or not Q is true. So this would be true regardless of whether we had, in this case, we could interpret or as inclusive or exclusive or, but for sentence 4, we've written it with an inclusive or. Sentence 5 then follows from sentence 4 and 1. We know that P or not Q is true from sentence 4, and therefore, plugging that into sentence 1, we can deduce that R is true, because if P or not Q is true, then R is true. This is, you may notice that this feels like a very formal and roundabout and effortful way to deduce things, and indeed it is in practice. As I also mentioned, though, computers are really good at this. So propositional logic does lend itself well to programmed implementation. There are many complications in doing that, but yes, indeed, computers are quite good at reasoning with propositional logic. So in this sense, this is a kind of logic that machines do well with. But even as we're talking about this, think of the title of Boole's book, which we saw in the previous slide. Boole's book was called The Laws of Thought. He was writing in the 1850s before there were any computers, and the way that he regarded logic was that this is the way not only that thinking should be, but that in a sense, good thinking is, that people reason with propositional logic and that they should reason with propositional logic. So the discussions around logic as applied to people are often an uneasy mix of descriptive and normative. Sometimes people want to argue that we do think logically, and sometimes people want to argue that even if we don't, we should. This is a good way of thinking. It certainly lends itself well to machine reasoning in many cases, not in all, but it often lends itself well to machine reasoning because it follows sets of formal rules that for people can often be stressful to follow in very, in ways that are free of mistakes. We often make mistakes. Machines are, when suitably programmed, can be very effective at doing this. You may have noticed that even in this reasoning, I made use of certain kinds of deductive steps. And in propositional logic, there are a number of these, but standard deductive step is called modus ponens. It's a very old rule in logic. And basically it says that if you know that if A then B is true, if you know that that's true, and you know that A is true, then you know that B is true. Sounds pretty straightforward. So the example on the slide, if there is fire, there is smoke. We know there is fire, therefore there is smoke. Okay? An equivalent rule, that is to say equivalent to modus ponens, means really the very same thing, but it goes by a different name. Modus tollens, it has a different syntactic structure where we could say if there is fire, there is smoke, and we know there is not smoke, therefore there is not fire. Because if there were fire, there would be smoke. Now, this is, to a machine, these two rules are essentially identical. They're making use, by the way, I mentioned the difference between inclusive and exclusive or. I should mention that in propositional logic, if A then B means something very specific. It's, in English, we often use if-then sentences in a kind of loose or informal way. But in propositional logic, when you say if A then B, what you mean is that will be true if A is true and B is true. It will also be, it is also true if not A is true and B is either true or false. In other words, if let's take this first sentence. If there is fire, there is smoke. If there is fire and there is smoke, that is sort of that's a good step for modus ponens. If there is not fire, we don't really know whether there is smoke or not. Or to put it another way, the only way that the sentence, if there is fire, there is smoke, could be wrong, the only way that sentence could be false is if it is the case that there is fire and there is not smoke. That would prove the sentence false. All other three possibilities, fire and smoke, not fire and smoke, not fire and not smoke, would allow the sentence to be true. So in propositional logic classes, people are very careful about interpreting if-then sentences. For example, the sentence, if Paris is the capital of Italy, then 2 equals 5. That is a true sentence. The first part of the if-then sentence is false. And from that point, it doesn't really matter whether the second part is true or false. If Paris is the capital of Italy, then 5 is a prime. That's also true because the first part is false. The only version of an if-then statement that can be false is if I say something like, if Paris is the capital of France, then 2 equals 5. That's a false statement because the first part is true, but the second part is false. Again, a long-winded way of explaining, but we have to be that long-winded to explain the nature of if-then in propositional logic as opposed to colloquial English. Modus ponens and modus tollens are both totally perfect deductions from two earlier sentences. They only have a very different, slightly different, I should say, syntactic structure. For a machine, these two things are essentially the same. For a person, they're not quite the same. People find it much easier to reason using modus ponens than they do using modus tollens. So that already should give us a hint that the ways in which typical computer programs deal with propositional logic and the ways in which people often informally deal with logic already have some differences to them. People also are prone to make mistakes in this kind of logic. So these are two examples of fallacies in logic, deductions that are not true, but that are tempting often because of the way we think of an if-then statement. So if we have a sentence like, if there is fire, there is smoke, and then we're told there is not fire, it is not correct to deduce that there is not smoke, because after all, there might be smoke for other reasons than fire. So this is called denial of the antecedent fallacy, and this is a form of faulty reasoning. So is the second example. If there is fire, there is smoke, and we know there is smoke, therefore there is fire. Incorrect. There could be smoke for other reasons than fire. So these are both examples of problematic or incorrect uses of logic that people are prone to. There are other kinds of mistakes, logical mistakes, that people are not prone to make. But the fact that we are prone to make certain kinds of logical mistakes, again, tells us that there's more to human reasoning than is expressed in the formal rules of logic. Even though Boole wanted to call his book The Laws of Thought, propositional logic doesn't seem to be the laws of thought. It seems to be an element, a sort of formal representation of certain kinds of effortful thought. But we don't follow the rules of propositional logic terribly faithfully. There's a classic experiment around these lines that was done back in the 1960s. And I will give this to you as an example. Here is the experiment. People are told that they're given 4 cards. And I've represented the 4 cards here in the slide. They are told that on one side of the card is a letter, and on the other side of the card is a number, okay? And then you are given a rule which your job is to test. You want to test this rule to see whether it's true or false, okay? So the rule that you're going to be given to test is, if there is an even number on one, or if a card has a vowel on one side, then it has an even number on the other side. Okay, so let me repeat that correctly. If a card has a vowel on one side, then it has an even number on the other side. And you are asked, given this set of 4 cards, to turn over exactly and only those cards that you would need to test whether this rule is true. So this takes some thinking when people do it, and they often make errors. I don't quite recall the statistics, but many people make errors in this task. As it turns out, you need to turn over exactly 2 cards. You need to turn over the E. If the card has a vowel on one side, then it has an even number on the other side. If you turn over the E and you find an odd number, you know the rule is false. The other card that you have to turn over is the 7. If you turn over the 7 and you find a vowel, like an A, then you know the rule is false. The other 2 cards you don't need to turn over, because no matter what you see on the other side, you won't learn anything about the truth or falseness of this rule. You won't learn anything about whether the rule happens to be true or false. If you turn over a K, then regardless of whether there's an even or odd number on the other side, doesn't tell you anything about this rule. If you turn over the 4, maybe you might see a vowel that would be consistent with the rule, but you may see a consonant that would also be consistent with the rule. So the only cards that you need to turn over are ones that could disprove the rule. In a sense, this is a tiny model of some philosophical treatments of scientific reasoning, in which the purpose for experiments is to disprove a theory. Most scientists don't feel that that's an accurate representation of scientific pursuit, but nonetheless, some people argue that when you do an experiment, it should be with an eye toward disproving a theory. In this case, turning over the E or turning over the 7 could disprove this rule. Turning over the other 2 could do nothing to disprove it. As I say, people have a lot of difficulty with this problem. But one interesting thing is that they have far less difficulty with what in some sense is an identical problem, an identically structured problem. But in this case, people have a much easier time solving the problem. And the distinction between people's performance in these 2 cases is interesting to speculate about. So here's the the new task. You're given 4 cards. Usually people say, imagine yourself as a bartender or something like that. You're given 4 cards. On one side of the card is the drink that a person is having. On the other side of the card is the person's age. And your job is to see whether this rule is true, that, or if you want to phrase it this way, whether this law is being upheld. If a person is drinking beer, then the person must be over 19 years of age. And your job is to turn over only and exactly those cards that will show whether the rule is being held to. Here, people have a much easier time. You turn over the drinking beer card. If the age on the other side is 16, then the rule is being violated. You turn over the 16-year-old card. If the person is drinking beer, the rule is being violated. The other 2 cards, you don't need to turn over. Because, for example, turning over the drinking Coke card can tell you nothing about whether the rule is being violated. Similarly with the 22-year-old person. So why is it that this task seems to be so much easier than the previous task involving letters and numbers? There are different explanations for this. There's not a unique explanation to it. The original experimenters who presented this version of the card task would make an argument that goes roughly as follows. We are very good reasoners when it comes to situations that are ecologically or evolutionarily realistic for us. Now, you might say being a bartender is not evolutionarily realistic, but seeing whether laws are being followed, seeing whether rules are being obeyed or violated, that is it's a venerable human activity in communities. We often care quite a bit about whether people in a community are obeying, the group laws, or whether they're not. So in this case, we might say that we're exercising not so much a kind of abstract talent for logic, but a rather specific talent, or rather specific human ability to detect cheaters in legal situations. That's not the only explanation for this distinction, but it's one explanation. In any event, just to leave you with this sort of reflection, what we've seen is that the ways in which people reason in situations that could be modeled logically doesn't seem to be quite the same as the ways in which, the formal rules of logic dictate, or pure mathematics dictates, or in fact the ways in which it is relatively easy to program machines. Machines can be made to follow logic reliably. For us, it seems to be more of a problem. We've spent some time talking about the computational view of problem solving that is in contrast and in comparison to the way that humans solve problems. We've looked at how understanding problem solving in machines can lend new insights into how we understand problem solving in people. Many of the problems that we looked at in that earlier discussion had to do with things like puzzles or fairly abstract mathematical problems or problems in the physical sciences. Those are very important types of problems that we often have to solve in a professional way. But now we're moving to a discussion of other kinds of, you might call them problem solving, but in the literature, they usually go by the names of tasks in judgment and decision making. Now, offhand, there are some gray areas between what we might call judgment and decision making on the one hand and problem solving on the other hand. So if we had to judge, let's take some archetypal situations which are thought of as judgment or decision making. You are in the market to buy a new car. So which kind of car are you going to get? That's a kind of decision-making problem. You have a number of distinct models of car. You could get a used car, you could get a new car, you could get cars of different makes and so forth. Which kind of car are you going to get? That's a decision-making problem. You might also think of it as a problem. You're going to search the space of choices that you could make and make one of them. But often we don't think of these, the kind of Rubik's Cube or puzzle problems in the same way that we think of decision-making problems. For one thing, decision-making in the literature usually has to do with situations that are broad, that are perhaps a little less well-defined than chess problems or Rubik's Cube, situations where we may have to make a decision with incomplete information or fairly quickly, situations where maybe the information is, you might think of it as incomplete, or you might think of it as just so enormous that we can't take into account all the potential information that we might have. We have to make some kind of decision based on all kinds of different factors. These are situations, if we were being uncharitable, we might say that problem-solving situations are the ones that are less realistic in our lives, and decision-making or judgment problems are the ones that often we care about in our lives. Should we take this course or that course? What should we major in? Having dated a person once, should we date them again? Is it worthwhile to invest in this house? All kinds of sort of large-scale important decisions in life get cast under this notion of judgment and decision-making. What that means also, because these situations are often more important to us, is that we don't have the sort of genial point of view about getting them wrong. Let me put it this way. If you're doing a Rubik's Cube and you fail to solve the problem, you may be frustrated, and it may matter to you. But you may, in talking to your friends, just say, I'm not very good at Rubik's Cube. That's life. What are you going to do? On the other hand, people don't feel that way about things like what they're going to major in, or who they're going to marry, or what city they're going to live in. I mean, people take those decisions pretty seriously, and they don't have they don't take a light view of themselves if they habitually get these things wrong. So it's like, well, I keep choosing the wrong profession. That has a more important ring to it than I can't solve Rubik's Cube. So when people talk about judgment and decision making and the ways in which people make judgments, there's a kind of, I refer to it here as a normative stance as opposed to a descriptive stance. We're not only interested in how people solve problems or how people make, in this case, how people make decisions. We're also kind of interested in the question of, are there continual mistakes or bad habits that come into our decision making? And are those linked? Can those be elucidated by a computational viewpoint? By looking at these decisions and judgments from the computational standpoint, can we understand not only the descriptive reasons that we make certain decisions, but can we improve the way that we make certain decisions. You could see the normative stances being important in classic problem solving as well. We'd like to learn how to solve Rubik's Cube and things like that. But it takes on a more urgent note when we're talking about things like, judging what kind of subject to major in, or a potential spouse, or a potential city to live in, or things like that. These are large-scale decisions, often with lots and lots of factors, and we'd like to avoid making, sort of easy mistakes anyway. So some of the judgment and decision-making literature has this flavor of what are the mistakes we make, and can we do better? Similarly, there's a distinction between problem solving and judgment and decision making. And again, it's not a hard and fast distinction, but a loose distinction between how we think of this evolutionarily. Puzzles, math problems, science problems, the sort of the staples of the problem solving literature, those feel to us like evolutionarily recent situations. It's not like we evolved having to solve problems in logic or abstract mathematics. These may be still very important to us in our lives, but things of this sort don't seem to have deep evolutionary roots. On the other hand, there are situations in judgment that you could argue have deep evolutionary roots. If you are encountering a new person, a person that you haven't seen before, are they a friend or a foe? What cues might you use to determine whether to be nervous around this new person or whether to be fairly accepting of this new person? If you meet up with an animal, is it a dangerous animal, or is it an animal that does not pose a threat? Perhaps it's an animal that could be prey for us. These are judgments that we make based on lots and lots of factors, and the idea of judgment and decision making is that it's something that we, as a species, we have evolved with certain ways of making these kinds of judgments, and often these techniques that we've evolved with serve us very well. They've evolved for a reason. We survived because we had these techniques of making judgments. However, the techniques that we evolved with may not be perfect, particularly for our situation now, that is the situation of our species now in, say, urban or developed environments. So we'll talk about some of these things. Let me begin by giving an example of the kind that illustrates some of the themes that come up in the judgment and decision-making literature. So this is an example of what can be called problem framing. It's also an example of certain kinds of economic decisions. And you may think of it as still being sort of mathematical, but it illustrates, you might call them difficulties that we have in making certain kinds of judgments. So imagine this situation this is an offer that's being made to you, okay? So you're being offered first a bonus of $300. I'm going to give you $300. And then you are asked to choose between the two following alternatives, okay? One or the other alternative, one of the other possibilities, what you're going to choose. Either to receive another $100 for sure, or to flip a coin. If you flip a coin, you get, if you win the toss, you get $200. If you lose the toss, you get nothing. Okay? So you think to yourself, what choice would you make? I've given you $300, and now I'm going to give you a choice between just taking another 100 or flipping a coin and receiving 200 if you win and 0 if you lose. In either case, you keep the original 300. Okay? Now, a little bit of, if you know anything about probability, you know that the expected value of both A and B, both choices A and B, is $400 at the end of the whole situation. In other words, in situation 1, you definitely have 400. In situation 2, you have a 50% chance of having 500 and a 50% chance of having 300. So you might think offhand there's no reason to choose between A and B, but that's not correct. I mean, you may have a very good reason for choosing A or B in this situation. The expected value of A and B is the same, but they're not identical situations. Okay? So think to yourself what you would choose in this situation. Now, here's a different situation. Let me pose this for you. I give you $500, and now I offer you 2 alternative possibilities. Possibility 1, I'm going to take $100 from you, back from you. In possibility, we'll call that C. In possibility D, you'll flip a coin. If you win the toss, you lose nothing. If you lose the toss, you have to pay $200. Okay? Now, think to yourself which of these 2 alternatives you would choose. Now, here's the interesting point. These 2 situations are, in fact, identical. The one that I showed you before, which I'll go back to here, that's really the very same situation as this one. In choice C here, you end up with 400 for sure. And in choice D, you have a 50% chance of having 500 and a 50% chance of having 300. That was the same, that was the same case for choices A and B. They feel different though. For a lot of people, and I confess this is true for me too, when you look at this choice, your mileage may vary, but I tend to look at this choice and think, I'll go for A. I'll take the additional $100 and end up with 400. In this case, I kind of think, I don't want to, you just gave me 500. I don't want to just give you back 100. I'll gamble to keep what I've got. Now, again, there may be a very good reason for choosing A over B or B over A. What there isn't is any kind of rational explanation offhand for why you would choose A in this situation and D in this situation. They are identical in the long term. At the end of the day, they're identical situations, and we shouldn't switch our decision merely because of the way the problem has been framed. So this is an example of problem framing, and for a lot of people, when they see an example of this kind, they get a little bit disturbed by it. Sort of like thinking, well, what's wrong with me? Maybe there's something wrong with the way I'm thinking about this. This is taking advantage, by the way, of a well-documented tendency in people's judgment, economic judgments, that they tend to value more the things that they already have as opposed to the things that they don't yet have but can bargain for. So once you own something, once I've given you that $500, there's a greater threshold to giving up some of it. In the first situation, I gave you only $300, and the idea of getting an additional 100 seemed attractive. This is one example of the kinds of interesting phenomena that turn up in judgment and decision making. Here's a related one. You could call it a kind of problem framing example. It's from a very fun book by cognitive scientist Dan Ariely. I think he describes himself as a behavioral economist. But in any event, here's the situation. It's a kind of problem framing problem, but this one is taken, I think, from real life. He describes it in the book, and this is an ad that he saw about subscriptions to the magazine The Economist. So notice the three choices that are being given here. The Economist, you could get a subscription to the website, to just economist.com, for $59. You can get a print subscription to The Economist for $125. You could get a print plus web subscription for $125. Now, you look at those three choices, and if you're like me anyway, the first thing you think is, what kind of lunatic would choose choice number 2, seeing as choice number 3 is the very same cost, but they're throwing in a $59 value for free. You get the print plus web subscription for the exact same cost that you would have for the print subscription. Why in heaven's name would anyone choose point number 2? And indeed, that's quite reasonable. There's a reason that the Economist gives you these three choices, however. They're intending for you to focus on the last two choices, and since it's an obvious decision between those last two choices, you would choose number 3, print plus web subscription. That's what they want you to choose. They would prefer you to choose print plus web subscription for $125 rather than just the web subscription. That's their preference. They're making this sub-choice easy for you. And so, in fact, people tend to disproportionately, when given three choices, two of which are easily comparable and one of those two is obviously better, people tend to choose the better of those two and ignore the third choice altogether. Is that rational? Well, there are reasons for it. There may be good reasons for it in human thinking. But in another respect, it's an example where our judgment is kind of being pushed in one direction or another. Ariely describes a very interesting experiment in his same discussion of this, and I'll see if I can describe it for you. It takes a little setting up, but he wanted to see if he could design a situation where people would sort of be prompted to make the choice that he wanted them to make by giving them a similar kind of three-way choice that The Economist does here. So here's what he did. First, he took lots of photos of, you could do this, by the way, as the mathematicians say, without loss of generality. You could do this with photos of men and women looking at photos of men, or you could do it with photos of women and men looking at photos of women. So apparently the phenomenon works the same. So we'll just say for description that we're dealing with photos of men, photos of males, and there are women looking at photos of males. And in this case, they're rating the photos by attractiveness, okay? So in the first phase of the experiment, you show many, many photos of males to female subjects and have them rate these photos according to attractiveness. Having done that, you now have, let's just say that you have two photos of two particular males. These are not famous people or anything. They're just photos of, random folks. But we have two photos of males, call them A and B, who in the first phase of the experiment have been found to be equally attractive. So without any other information, if you were to take a new female subject and show her photos of A and B, you might expect about a 50-50 chance that you would find A more attractive than B or vice versa. Now here's what Ariely did. He took some of these photos and, hold on. He took some of these photos. Let's take the photo A and the photo B. And remember, these are sort of equally attractive folks. And he used a little bit of Photoshop on one or another of these photos. So let's say that we take A and we do a Photoshop on photo A to produce a new photo. We'll call it A prime. Now, this being, a psychological experiment, the photo of A is morphed a little bit to, let's say, to be a little asymmetric, or the face, the head shape is a little odd, or something like that. In other words, A prime looks kind of like A, but less attractive. Okay? Now, if you show these 3 photos to a new female subject, someone who hasn't been involved in the first part of the experiment, you show her A prime, and B, and you ask which of these 3 people is most attractive. If the choice A prime had not been presented, you would expect about a 50-50 chance that she would choose A or B. However, the photo A prime here acts kind of like choice 2 in the economist situation. So she looks at these 3 photos and is much more likely to choose A. A prime is like that print subscription to The Economist. No one's going to choose A prime, but the choice between A and A prime is easy. And so the focus is driven to make a choice between A and A prime. Similarly, if you do not show the photo A prime, but do a similar kind of Photoshop job, and now show A, B, and B prime to a new female subject, she'll be much more likely to choose B. Again, B prime is the choice between B and B prime is easy, and the focus is then made on this easy choice, and it is much more likely that she'll choose B than A. So what would have been a fairly difficult or delicate decision between A and B can be made to be an almost automatic decision by giving an irrelevant third choice that somehow drives attention toward one choice or the other. That's pretty interesting. Now you might think, again, that's irrational. By the way, Ariely says there's a lesson in this. If you are going out looking for a date, again, whether you're male or female, if you're going out looking for a date, maybe going to a bar or a party or something, he says it's a good idea to bring along somebody who looks just like you, but a little less attractive. That may work. Of course, you don't want to tell the other person that's why you're inviting them. But anyway, that would sort of fall into the category of this kind of problem framing. Now, again, when some people look at examples like this, like the economist example or this photo experiment, they get a little disturbed about it. What it means is that their judgment is perhaps not as foolproof as they felt it was going to be. And this is where this normative side of judgment and decision making comes in. We'd like our judgment to be, if we want to put it this way, as rational as possible. We'd like to be able to explain to ourselves why we made certain judgments. And we'd like those explanations to feel as though they're sort of in accord with what we think of as reason. this is often rather difficult. Reason is a kind of slippery concept in situations like this. We may begin by asking, are these really mistakes altogether? Maybe we don't want to think of them as mistakes. Maybe there's a certain kind of sense in that first situation. If you have a certain amount of money, or if you have an object, maybe there are good reasons why you should work harder to keep what you have and be less willing to give it up than in situations where you don't have something and you might gamble to get a bit more. In other words, maybe there are good reasons that you should value what you own already with sort of place a greater value on those objects than on objects that you don't have. That may not be a mistake. But if they are mistakes, if we want to cast them as mistakes, what are the mechanisms that cause us to make them? Those are really interesting questions. Could we mimic those processes in a machine? Or could we make machines that make judgments which are less prone to human-type errors? Those are sort of twin questions about this sort of thing. And this last example gives rise to yet another question, which is should we be worried that others, perhaps others whose interests are not aligned with ours, are trying to do things to manipulate our decision-making? The economist in Ariely's example was trying to manipulate the situation so that you would make a particular choice. Now, you may end up being happy with that choice, but it's clear that the economist's point of view on your decision and yours are not identical. So now we deal with the situation where other people or institutions can exploit the properties of our decision making. Those are questions that we need to deal with as we discuss the subject of judgment and decision making in general. While we're on the subject of judgment and decision making, we began talking about some of the issues involved in human judgment and decision making, and we contrasted those with some of the issues, the ways in which we discussed this from a computational viewpoint when we were talking about more sort of abstract problem solving. What I want to do right now in this particular session is describe a couple more examples of what have been called heuristics and biases in judgment. Much of the sort of pioneering literature on this, a lot of the original work was done by Daniel Kahneman and Amos Tversky. Kahneman recently, a few years ago, wrote a very interesting book called Thinking Fast and Slow, which is kind of a compendium of a lot of the work that he and Tversky, who died some years ago, the book is a compendium of the work that Kahneman and Tversky did together, and much of the research that they did on certain kinds of heuristics and biases that people use in making decisions or rendering judgments. Now, the word heuristic, again, is sort of a description of a kind of rule of thumb, a computational, a sort of computational technique that we can use that will help us solve problems, but is not guaranteed to solve problems. So heuristics are things that we can try that are often good ideas, not always, but ways in which we can, sort of approach a particular problem. our association with words like bias is more negative, the idea being that we have certain ways of thinking about judgments and these cloud our judgment. In any event, you'll get a sense of some of the phenomena. What I'm going to try and describe are just a couple of the sort of standard experiments that are used to demonstrate these sorts of phenomena in judgment. So here's an example. This is actually it's a much discussed and somewhat controversial example. When Kahneman wrote about it in his book, he mentioned that this particular example and the ones along these same lines has garnered the most sort of debate about its importance, what it means, whether it's a problem. Let me show it to you first. It goes by a general name called the conjunction effect. And the idea is here you first see a description of a person. So you're given a little story about this person, Bill. Bill is 34 years old. He is intelligent, but unimaginative, compulsive, and generally lifeless. In school, he was strong in mathematics, but weak in social studies and humanities. Okay, that's the description you're given of Bill. And now you're given a collection of statements about Bill, like these, and your job is to rank order these statements from most to least probable. That's the idea. So you take these statements about Bill and you order them from most to least probable. Now, when people think about that description of Bill and they look at these statements about Bill, stereotypes being what they are, people often tend to, assume that perhaps Bill is an accountant. Fairly reasonable. They don't think that it's especially likely, for example, that Bill plays jazz for a hobby. The three statements that we're interested in here, the others are, sort of like additional choices, but the three statements for us to focus on here are Bill is an accountant, Bill plays jazz for a hobby, and Bill is an accountant who plays jazz for a hobby. Now here's the thing. When people answer this question, they rank Bill is an accountant as most probable, Bill is an accountant who plays jazz for a hobby as next most probable, and Bill plays jazz for a hobby as least probable. In other words, they view this statement as more likely than this statement. Now, mathematically, that's impossible. If you think about if you think about it from the standpoint of set theory, imagine all the situations in which Bill is an accountant and Bill plays jazz for a hobby, and Bill is an accountant who plays jazz for a hobby. If he is an accountant who plays jazz for a hobby, that's a subset, a smaller number of situations, a much smaller number of situations than all the situations in which Bill plays jazz for a hobby. In other words, it simply can't be more probable that Bill is an accountant who plays jazz for a hobby than that he simply plays jazz for a hobby. It can't be more probable. The number of situations in which this is true is a small subset of the situations in which this is true. However, people view this as more probable. Now, when people see this example, me included, I sort of read this example, thought about it. Yeah, of course, once you think about it, it has to be more likely that Bill plays jazz for a hobby than that he plays jazz for a hobby and he has a particular profession. Sometimes people look at this and they think, well, the difficulty is kind of the word probable. What do you mean by probable? People might not, for example, be interpreting this question as given 10 million distinct situations in the world, rank order the frequency in which they occur. What they may be responding to, at least what what many students, when they see this problem, what people may be responding to is not so much what's probable mathematically as where do you think this story is going? What's a probable ending to this story? That's a fuzzier question, but you might reason that why are you telling me these things about Bill unless you're telling me something that is informative or archetypal about the kind of profession that he has. So, maybe you could argue back and forth about what probability, how a word like probability is interpreted for something like this. And indeed, questions about probability are pervasive in the judgment and decision-making literature and how we interpret probability. Probability is actually a rather remarkable and complex and many mathematicians would say beautiful area of mathematics, but it's one that has controversies associated with it about how to interpret probability. So not everyone interprets probability in the same way. It should also be mentioned that the notations for the formal discussion of probability is relatively young in human affairs. That is to say, you could trace it back to people like, say, Pascal, who wrote about probability in the 1600s. Now, the 1600s may feel to us like, oh, that's a long time ago. It's not all that long ago, 300-400 years ago. So we're dealing with things, ideas about probability that we did not evolve with. Therefore, when we look at questions that involve some kind of probability, often we are dealing with concepts that are relatively new in human experience. Let me give you another example of a similar kind of problem that is cited in the discussion and in the judgment and decision-making, in the judgment and decision-making literature. So here's another description of somebody, not Bill, different person, Steve. Steve has some similarities with Bill, but let's ignore those. Steve is very shy and withdrawn, invariably helpful, but with little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. And now you're asked to rank order the probability that Steve has one of these professions. Is Steve an architect, farmer, librarian, biologist, or taxi driver? Now, again, this is the issue here is somewhat different than it was in the previous example. When people look at these choices, and again, thinking in terms of stereotypes, they often hone in on the idea that Steve is a librarian. Seems like the kind of person who might be a librarian. So they decide that, librarian is the most probable choice for Steve's profession. Now, one way of looking at this question, though, is to say, really and truly, given what we know, let's assume that we're dealing with the population of adult men in America. What's the most probable profession for Steve, given this description? Well, let's just put it this way. Agriculture is not the prominent profession that it used to be in America, but it's still a pretty important profession. And the number of, let us ignore the description of Steve for the moment and just look at these 5 professions and say, without any information at all, where are the numbers? I mean, what are the most likely of these professions? Certainly, it is much more likely for a randomly chosen adult man in America to be a farmer than to be a librarian. There may not be nearly as many farmers as there used to be, but there's still lots more farmers than librarians around. So, one way of thinking about this, going back to the original question, is to say, well, Steve could be a typical librarian, or he could be a fairly shy, orderly farmer. And since there are, who knows, let's say 500 times more farmers than there are librarians, it may really be much more likely that Steve is a farmer, even a somewhat unusual farmer, than that he is a fairly typical librarian. These are called, the idea being introduced here is one of what is sometimes called base rates in probability reasoning. Without any other information, given no information, we would find it much more likely if we were choosing a random person out of a huge urn and we were just, taking descriptions of people, adult males in America out of a huge urn. It's much more likely that we'll choose a farmer than a librarian. If this happens to be a description of a farmer, that may still be much more likely than that we have chosen a description of a librarian. So again, this is not something that people generally take into account when dealing with a situation like this. Kahneman and Tversky argue that we have a sort of blind spot when it comes to these base rates, and that this can cost us in certain kinds of decision-making situations. We'll get back to discussions of that idea, but let me show you a couple of other phenomena. One is called, it has to do usually with, it's usually put forward in situations that involve numbers or quantities, needn't always, but it's called anchoring. And this is an example of the kind of question that displays anchoring when people try to answer it. So you take a population of subjects and you ask them a question like, was Ronald Reagan 120 years old when he died? Or was Ronald Reagan 50 years old when he died? Now, both those answers are wrong, and the answer is no in both cases. When people see these questions, they know, well, Reagan lived to well past 50 years old, and just about nobody lives to 120 years old. So when they look at these two questions, they answer no. But then, in both cases, if you ask the person a subsequent question, how old was he when he died? The people who are asked the first question will reliably give you a larger number, an older number, than the people who are asked the second question. In other words, when people are asked the first question and then they say, no, Reagan was not 120, you ask them, how old was he when he died? And it appears that what they're doing, more or less, to a good approximation, is taking the original number of 120 and reasoning downward from it, moving downward until they find a number where they think that might be the age at which Reagan died. In the second case, they're taking the number 50 and moving upward until they think they've got a reasonable number. In both cases, what people do is they end up with an age guess that is closer to the number, if you want to put it this way, the number that they were primed with. So you give people this question and you can move their numeric judgment in one way or another by getting them to start from an original position, an anchoring position. So this is an example of what could be called a bias in judgment, and one that might be exploited in other situations. Here's another example. It's an example that draws on research from memory, from the studies of memories, of recall of words and facts and so forth. So people are asked this question: estimate the proportion of English words that begin with the letter K versus words that have a K in the third position. Now, as it turns out, there are more words in English with K in the third position than there are words with K in the first position. However, the structure of our memory for words seems to be kind of indexed by first letter, maybe first sound. In any event, when people are asked to come up with words, that either have K in the third position or K in the first position, they find it easier to come up with words with K in the first position. That's an easier job. They can sort of think of the words that they know that begin with K. It takes more effort to think of the words that we know with K in the third position. So in this case, even though the correct answer is there are more words with K in the third position, the words that begin with K are more available to us, more available to our memories. And that leads us to make a mistake in answering this question. You could view it as a mistake in judgment. Okay. These are just a few of the examples of the literature and judgment and decision making. And you notice that many of these examples have this flavor that you can present people with situations where it then appears that people are making foolish decisions. Now, the question of whether these are really bad decisions, whether this is really a problem for us, that itself is a matter of some debate. There are researchers who feel that these are not especially important or dire problems in judgment for us. Maybe that, in some sense, we don't even want to call them mistakes. But if we do want to call them mistakes, are they terribly important? If they are important, why do we make them, and can we train ourselves not to make them? Some people in the literature describe these as illusions, analogous to optical illusions, which means that they could be fairly pessimistic about the idea that we can train ourselves not to make these errors. When we see certain kinds of optical illusions, even if we know that there's an illusion, take illusions where you see two lines which happen to be the same length, but here, I'll draw one for you. The famous Muller-Lyer illusion. I don't know if I'm doing it perfectly, but here's the idea. You're given these two lines, one of which has arrowheads pointing inward on the ends, and the other has sort of, if you want to call them that, arrowheads pointing outward. And the lines are the same length, but often when we look at these two lines, we view this one as being smaller and this one as being longer. Okay? It's hard to train yourself out of that illusion. It's not a question of, you may even know intellectually that the two lines are the same length, and yet when you look at the picture, you keep saying to yourself, they look like they're different lengths. I can't help myself. Some people describe the phenomena involving judgment and decision making in a similar way, that we might even know that this is an error, but we can't quite help ourselves. So that leads to other questions about whether, even if we know that we're making these errors, can we fix it? A related question is, can we design machines, can we design programs whose heuristics or biases are different than those that we have, or that are perhaps more mathematically rigorous, or use different internal models of probability than the ones that we typically use? Can we design programs that are far less likely to make these kinds of errors than human beings are? Those are interesting questions. And as we continue to talk about the judgment and decision-making literature, we'll touch on some of these debates.